included the definition of corona charge in this slide, which we discussed last time. So, corona charge means, as we know in electrostatic precipitator, the basic principle is to charge the particle of like charge the particle with opposite charge to the collecting plate, right? So if the collecting plate is positively charged, then the particle should be negatively charged, so that the particle will migrate towards the collecting plate and they will be collected. In order to achieve this, uh, first the voltage is provided to the mesh or the discharging electrode, and this amount of voltage should be enough to ionize the gas molecule around the mesh. This ionization process results in a kind of, you can see on the left hand right hand side, there is a illumination around the mesh, wire mesh. Okay, so this is called the corona zone, where ions are present around the wire mesh, and because of that there is a illumination, or the light, you can see the light around that, in that zone. This zone is called corona zone, and this process is called ionization process. Due to ionization of gas molecule, there are possibility of two type of particle charging mechanism. Hello. Okay, all of you mute your microphones. Just mute your microphones. Ankush Arora, mute your microphone. If you have question, raise your hand. Okay, but keep your microphone muted, so there would be no disturbance. Okay, after the ionization of the gas molecule around the wire mesh or discharging electrode, uh, the the particle which are passing through this zone get two kind of discharge through two kind of mechanism, you can say. The one mechanism, or first mechanism, which is dominant, is field charging, and the second mechanism is diffusion charging. Field charging is actually important when the particle size are large, probably greater than 2 micrometer. Maybe in other book some other value might have been given. And diffusion charging is important when the particle size is very small. Okay, when the particle size decreases. Now, is that clear what is corona charge and all? Who asked question last time? Just confirm if you are there.
Yes, ma'am.
Okay. Now in field charging, the particles are bombarded by the ions, and it continues until the ion will be saturated with negative charge, and therefore the electrical line around that charged particle will change their direction because of the repulsion. Okay, so this field charging process makes the particles saturated with the charge. Okay, but if the particles are very small, then the diffusion charging may takes place, and this is because of the random or Brownian motion of the gas molecule, and therefore they you can say govern the motion of the ions. Okay, and because of this random motion of ions, which is produced by the thermal motion of surrounding gases, the particle get charged, and these are for this particular charging is for small size particle. So I have explained it here in more detail, and the same thing I have told you just now. For kinetic, for diffusion charging, kinetic theory of gases can be applied to understand the charging phenomena. This is field charging. The spelling is wrong. I will correct this.
नहीं मतलब उसके बाद
So
क्लास में
all the important point I have already told you. Advantage, disadvantage we have seen. Now this slide shows the formula for calculation of charge on particle due to field charging and diffusion charging. uh, we are not learning the derivation of this formula. I tried to find out the derivation, but it's very complicated. Even the book which I am referring here is Wong et al., edited by Wong, Teria, and Huang. This book, which is Air Pollution Control Engineering, is the latest book I have on this topic. However, the the derivation is very complicated. So I am not including the derivation of this formula in your course. So for field charging, the saturation or the maximum charge a particle will carry can be given by 4 into pi into k0 into p into a square into e0. Okay, where capital K0 is permittivity of the free space, which is already known. Like you all must have learnt about that in electrical engineering and even in 12th class. P is the measure of field distortion as a result of particle charge. So as I said, because one the particle will get saturation charge, the electrical field around the particle will get distorted, right? The line will repel, the electrical line or electrical field will repel from the particle. So that distortion can be given by 3d upon d plus 2, where d is the electric dielectric constant, and p can vary from 1 for no distortion to 3 for the large value of dielectric constant. Okay, so this is how p can vary from 1 to 3. A is the particle radius, capital E0 is the uniform corona discharge, field intensity means volt per meter in terms of intensity, right? So particle charge as a function of time can be given by qf at any time t. Oh, 1 minute, I will put the pointer. Is equal to q maximum, q maximum into t upon t plus tau. So this is t plus tau, where tau is particle charging time constant. That means the time required for 50% of maximum charge to be acquired by the particle. Okay, so T can be calculated, or QF, the charge on particle at any time T, can be calculated using this formula. Tau can be given by 4 into K0 upon Qi into Mi into N0, where Qi, K0 we have already learned. Qi is the charge on an ion, which should be 1.602 into 10 raised to minus 19 coulomb. Mi, ionic mobility in meter square per volt per second. N is N0, it should be N0. Okay, and there are two N. So one is N is the ion density or concentration at any time and at any given time. N0 is the initial ion density or concentration. U, capital U is also, so capital U and all this thing will come in diffusion charging. So diffusion charging, as we already discussed, is because of the Brownian motion, or you can say random motion of the gas molecule, because of the thermal gradient, and that results in like the interaction between the particle and the charge in such a way that is the that can can be categorized under diffusion charge. Okay, so and according to kinetic theory of gas, ion density of the gas in potential field varies as n is equal to, so ion density can be given by n is equal to n0 into exponential of u upon k into t, where u is ion potential energy, um, K is Boltzmann constant, T is the absolute temperature, and R, okay, so R will come in the formula of U, okay. So U can be calculated using Q into QI we know, upon 4 pi into K0 into R, where Q is again the charge on ion, but I think this is Qi is the charge on ion. Small q is given here, or I forgot to write q, small q. Okay, we will learn what is small q. I will put the small q also here. Uh, we will see the example, then it would be more clear. Okay, so q into qi upon this is the formula qd, which is the total charge due to diffusion, can be given by using the u, and means the derivation will use u and n, the density of the ions, and this is the final formula. This formula will be available to you because it's a open book exam, and you can see the formula and solve the question. So here the number of ions that strike the particle per second in diffusion charging can be given by pi into a square into capital N into Vi. Vi is root mean square velocity of the ion. Time interval is given by this formula, and then K, I have already told you what is K, Boltzmann constant. So this example will fully clarify what how to put the value, which value uh, means I ask you to go through the unit balance in order to understand um, the the like in which term you need to put the value, because unit might be different in your problem, so you have to be careful about the units. Okay, so this example is already solved on in this PPT. You can go through the example, and it's just application of simple all the formulas given in the previous slide. So I'm not going through it. Do you have any question regarding what we have learned? Anyone? Okay. If there is no question, then efficiency of ESP efficiency can be given by two formula. There are two different formula can be used. Efficiency is equal to 1 minus exponent of A into W upon QG, or 1 minus exponent of K dash into PC upon QG, where A collection area of the plate, collecting plate. So there are two plates. One is discharge plate, other is collecting plate. Okay, this is the simple ESP where plates and mesh are used. However, there would be cylindrical electrodes also. So there another type of ESP may have cylindrical you can say electrode for discharge and collection of the particle. So I just forgot to show you the arrangement of the plates in ESP. I have put one figure from, let me just show you. Yeah, so you can see on the right hand side, right? This is how the plates are arranged in ESP. So it's not a simple unit, it's like huge unit, okay? So it's not like putting the plate in some fashion will work. It's like all calculated. The distance between the plates are calculated, and they are arranged in a such a way that maximum efficiency can be achieved. Okay, so having said that, we will see that the efficiency of the ESP can be calculated using this formula, and QG is the gas flow rate where, right? W migration velocity can be given by this two formula. If you know the E0 and A and mu, where mu is dynamic viscosity of the gas, then formula 1 can be used. Q is the charge in coulomb, E0 the electrical field intensity, etc. While if you know the corona charge, okay, or corona power, then the other formula can be used. So this formula you can go through it. It's not difficult. It's very easy formula. Now here is another example of ESP, and this is also a simple example. Just PC by Q is the gas flow rate is given in this example. The gas flow rate is 9,000 meter cube per minute for 99.8% efficiency. Estimate the power requirement. So PC need to be estimated. So it's a very simple thing. Already PC upon Q is given. Okay, this is another problem. You can solve this problem using the formula given in previous slides. And I have put the hint also. Double the number of plate will double. So there is other part, second part of this numerical, which says what is the effect of reducing the plate spacing to one half of its current value and doubling the number of plates. So how much efficiency will increase because of that, or decrease, or whatever. So doubling the number of plate will double the collection surface area. Reducing the distance between the plate will double the field intensity, right? So using this, you can solve the problem and find out how much efficiency has changed in second case compared to the first case. Application of ESP we have already learned. I would encourage you to go through the different research paper, maybe, or maybe the case studies provided on various websites related to performance of ESP in all these industries, and have this information with you, because you may have some general question in your exam which are not directly from what we are learning using the PPT. So some questions which would be related to your course but may not be directly related to what we are learning in the class. Okay, so it's an application of your learning in the class. So at least go through this number of industries listed here and find out if there are case studies available on internet. So for filters, we have already learned about the baghouse filter and liquid scrubber. I think I have explained the liquid scrubber also last time. Problem is here cyclone we wanted to start. So cyclone is another device which is very robust device and generally used where the flue gas is heavily loaded with the dust particle. So because it doesn't require any electricity, any kind of, there is no digital or electrical part in this particular device. It's just a mechanical device. It's very cheap, it's low cost control, and efficient for basically large size of particle. It is very efficient, even though like small size particle can also be collected, but for collection of particles less than greater than 10 micrometer can be achieved very efficiently in using this device. Inertial character, no moving parts. So I already told you the particulate laden gas is accelerated through the spiral motion, which imparts a centrifugal force to the particle. The particle are hurled out of the spinning gas and impact on the cylindrical wall of the cyclone. Then they slide to the bottom of the cone. So because of the like spiral motion or vortex motion inside the device, the particle which are heavy, they have enough gravity, they are not able to follow the vortex motion, and they just impact on wall, and they drop down in the bottom hopper. In order to design the cyclone, this is like the dimension is given here. The whole design depends upon the barrel diameter, which is D2, the diameter of the top part of the cyclone, and the DE, which is from where the clean gas comes out. So here all the formula are given in terms of D2, right? So barrel diameter D2, length of the cylinder D2 D2, length of the cone means this one L2 is given by 2D2, and so on. DE, which is the diameter of exit from where the clean gas goes out, 0.5 D2, height of the entrance, which is like from where the gas goes inside the cyclone and go through the spiral or vortex motion in the downward and upward direction, is 0.5 D2. No, it's where is H, yeah, 0.5 D2 again. Width of the entrance is 0.25 D2. What is the difference between B and H? Can you see here B? I don't think B is given. How come B? Oh, yeah, okay. So see, this is like, this would be B. The here it is shown, right? So there is H, which is vertical height of this inlet. B is the width of the inlet. Okay, so width of the entrance, diameter of the dust, diameter of the dust exit, which is D. I think it's not shown here. DE is shown here, but
It
diameter
is
of the dust.
the
DD is given below.
Yeah, this hopper one, right? DD is 0.25 D2, so hopper this one, right? I think I have to make this figure colorful, so it will be more, it will be easy to follow. Length L3 is given as 0.125 D2, and L3, can you locate L3? Yeah, this one. Okay, so L3 is given here. So once you know the particle size ratio, which is the given particle size divided by particle size for which 50% collection efficiency, for which this particular device can give 50% collection efficiency, then you can calculate the collection efficiency for a given size particle dp using this characteristic curve of cyclone. Is that clear? So dp is the given particle diameter, and dp50 is the diameter of the particle for which the collection efficiency is 50% for a given cyclone, of a given cyclone, you can say. So d by d50 is known, then you can calculate the collection efficiency of the cyclone for a given size particle. Okay, so here d50 can be calculated using this formula for a cyclone. So actually what um, I would say, we choose, for example, if I know from a source, say brick kiln, okay, there is a size distribution of the particle, and the size varies from 10 nanometer to say 8 maybe 2.5 micrometer or 3 micrometer. So it's a wide range of the particles are there, right? So when you apply the cyclone in such a source, and almost all the air pollution sources are of similar type, the whenever combustion happens, the particle of a large range size range are emitted in the atmosphere. So in that case, you can go you can measure the number size distribution and mass size distribution of the particle, and depending upon what is the peak concentration for and corresponding diameter, we can. So I will try to explain it in on board if possible. uh, I don't have board here. So can you see my cursor? Did
Yes,
you
ma'am.
do you remember that we said the air pollution concentration coming out from the stack follow the log normal distribution or Gaussian distribution, right? Similarly, for particulate matter, you can measure the number of different size of particle using advanced instrument, as well as the mass of the different size of particle using some other instrument. Once you know the number size distribution or mass size distribution, and when you plot that distribution, you will find that there is a peak concentration, number concentration or mass concentration corresponding to certain particle size. If you try to remove or control that particle size by at least 50%, then that would be your dp50. So once knowing your dp50, okay, where I want to collect at least 50% of this particle, I want to remove at least 50% of this particle or this particle size or whatever, then BH etc can also be calculated, given like one value can be assumed. Say I assume the width of I assume the height of the cyclone as say 10 centimeter or 20. So there are cyclone which can be of height, um, I think in our lab we have maybe 15 centimeter cyclone, and there could be the cyclone which are used in industries, could be of few meter in size. So from few centimeter to few meter, and the size will vary with the particle removal, or the size of the particle you want to remove. Okay, so I don't have picture of cyclone which we use in the lab, but I will put that picture here, and you will see, and even the dimension of the cyclone. So you will see it's a very small cyclone, and in industry the cyclone used is very high because gas flow rate is high, and also it depends upon what like what size of particle you want to remove. So knowing that dp50 can be calculated for a given dp50, even b or h can be calculated if some other parameters are given. Then theta is actually effective number of turns made in traversing the cyclone. So the vortex number of vortex, you can say coil, that can happen inside the cyclone, that is theta, effective number of turns made in traversing the cyclone, and that can be given by pi by h into 2L1 plus L2. So L1, L2, all I have explained, right? Is the length of the cylinder, and
Ma'am, you told like if we find the size distribution of the particle.
Length of cylinder and the cone respectively. Okay. Is there any question?
Uh, Ma'am, as you told it for it will
Uh-huh.
depend upon the size of the particle that which type of cyclone we have to use.
Uh-huh.
So, ma'am, for small size particles, we have to use small cyclone or large cyclone.
No, no. See, for a small size particle, say for example, for PM, so it depends not only on the size of the particle but also on the gas flow rate. Okay. So, for say to remove or to segregate the 2.5 micrometer diameter particle from atmosphere and collect that particle, the cyclone we use is very small. Okay, but for similar collection in large industries, probably the large size cyclone are being used. So in general, when you go, okay, so in general, when you see the collection efficiency figure, um, okay, so here I don't have the figure which shows the um, flow rate versus collection efficiency, right? So I will tell you that even for a given cyclone, say we can change the collection of particle size by changing the gas flow rate. Okay, so for example, we have a cyclone where it can work and segregate the particle less than 2.5 micrometer diameter at 5 lpm, right? But if I want to collect 1 micrometer particle or particle less than 1 micrometer in size, then I have to increase the flow rate. Okay, so what will happen if I increase the gas flow rate? So the very small particle which are less than 1 micrometer in diameter will not settle down, but the particle larger than 1 micrometer diameter which have enough mass or inertia, they drop down and they would be removed from the gas stream. So with increase in gas flow rate also, you can increase the you can change the size of the particle that needs to be collected. So this is just one characteristics we have shown here in this. Can you see still? Are you able to see my PPT?
Yes, ma'am.
Okay, so
Yes, ma'am.
this one characteristic is shown here, but I will also put the characteristics where the flow rate, you can change the gas flow rate and you can define the size of the particle to be segregated. So that is also possible because it all depends upon the vortex motion. So size of the cyclone, size of the particle to be collected depends upon all this factor. What is the gas flow rate? What is the size of the cyclone? Sometime even the given size of the cyclone may not be sufficient to collect the particle of a particular size. I would put more information to explain this phenomena. Okay, because this question I think in last time nobody asked me this question, so I just did not put it, but I will put it. So you understand, like the size segregation or the size collection size can be changed by changing the flow rate. Is that clear?
Yes, ma'am.
Okay. So this is how this is one example, and it's very simple example. Um, Here, the determine the efficiency of a standard cyclone having following characteristics of particle, uh, 10 micrometer in diameter with the density 800 kg per meter cube. Cyclone barrel diameter is given, gas flow rate is given, and gas temperature is given. effective number of turns you can find out, and then you can find out various dimension. Then D50 can be calculated. So D50 of for a given cyclone is 7.32 micrometer, right? And we want to remove the particle of 10 micrometer in size for a given gas flow rate. The flow rate is constant. You are not increasing the flow rate because the flow, this gas is coming out from a certain industry, and it depends upon how much fuel is burned, or the burn rate of the fuel and air to fuel mixing, right? Just an example, brick kiln could have two type of you can say mechanism, where you will have the natural draft, um, natural draft gas flow in the stack, or you may have a forced draft flow. Okay, so in case of forced draft flow, this gas flow rate would be higher than the natural draft flow. Okay, so here when we are applying the cyclone in an industry, the gas flow rate will be constant depending upon the stack velocity of gas, right? In the industry, in that industry. However, when we measure the particle or segregate the particle in the atmosphere, we can change the suction pressure out on the exit of the cyclone, okay, in order to increase or decrease the velocity inside the cyclone. And that is why we can achieve the different size particle segregation when we are talking about the atmospheric gases. Okay, collection of the atmospheric particle. This can be done in the industry. It's not like I'm not saying it cannot be done in the industry. You can change the gas flow rate in the industry by providing forced draft, and you change the gas flow rate, and you can change the collection size of for the cyclone. But this is some just a simple example where the gas flow rate is given, which is constant throughout. Means you can assume this is the gas flow rate. It always remains like that. And D50 can be calculated for given particle diameter of 10 micrometer, 10 by 7.32, which is 1.37. Therefore, efficiency can be calculated from here. So you can see the cyclone efficiency is not that great, but like if you will see, maybe for larger size of particle greater than 10 micrometer in diameter, say 70 micrometer diameter particle, the efficiency will be very high, right? Because this is 70 upon 7.32, it would be around 10, and the efficiency of those size of particle will be around 100%. So the efficiency will vary with the particle size.
Ma'am,
Yes.
in the previous problem, it is given that the density of particle is 800 kg per meter cube. So, this is the density of the contaminated air, or is it something else?
Oh, okay. So, see, as I told you, uh, all these control devices we are learning is for industry. So, say there is a industry where some steel cutting is going on, okay, or metal cutting is going on, and the density of that metal is 800 or 1000 or 1400 kg per meter cube. So that is one way. Sometimes this may come, but in this case, where was that? Here, I think it's a, yeah, diameter with the density. This is the density of the particle, not of the gas. Okay, so this is not of the gas.
Okay, means ma'am, if it is from the steel industry, then we consider here the density of steel because
Yeah,
the main
yeah.
particle is of ferrous.
Or maybe in marble industry, the marble particles are coming out, and the density of those particles will be very different than on an average you can say atmospheric air density. So I would also like to tell you, in case of atmospheric aerosol, when we segregate the atmospheric aerosol, the density of the particle and the density of the gas can be considered around 1.2, 1.3 gram per cc. Okay. Okay, for atmospheric particle, the density or particle, or you can say the mixture of particle and gas, the density is almost same, we assume, because it is means the studies have found it is not much different. So but whether it's a density of the whole gas containing the particle or density of the particle, it is around 1.3, 1.26 sometimes gram per cc. For Delhi, the particle density was observed as 1.26. Okay, 1.26 gram per cc. So when we consider the atmospheric particle, it's very different. Hmm? Okay. Now absorption. Absorption is a phenomena. It's a adsorption is a physical characteristics where you know the difference between adsorption and absorption. So I will just explain adsorption first. What is adsorption? Adsorption is a physical phenomena where some metal or some molecule can get attached to the surface of existing particle or molecule or whatever, and there is a just like attraction force between these two entity, while absorption is, it will include the chemical phenomena also. So control devices based on absorption converts the gaseous pollutant to liquid. Okay, so mass transfer process in which the gas dissolves in liquid. So it's a, as I said, it's a chemical reaction or chemical phenomena. So for example, I told you in earlier classes also, if sulfur dioxide, nitrogen oxide is coming out from any stack or any industry, and if water or is present in the atmosphere, it will react with water. It's a aqueous phase chemistry, we say, and it will form H2SO4, right? If ammonia is present there, then H2SO4 will react with ammonia and it will form ammonium sulfate, ammonium nitrate, and so on. Mass transfer is a diffusion process wherein the gas moves from higher concentration to lower concentration. The removal of the pollutant gas takes place in the three steps. So these three steps are diffusion of the pollutant gas to the surface of the liquid, transfer across the gas liquid interface, which is dissolution, and diffusion of the dissolved gas away from the interface into the liquid. So there are three kind of diffusion, though two kind of diffusion can take place, and one is dissolution. So however, like through this mechanism, the gas and the liquid react with each other and they form a different product, and that can be removed by collecting, like using a collection device. Spray chamber and towers or columns are devices for absorption. So spray chamber means you can spray some kind of liquid, water or other liquid, in order to um, uh, you can say start the chemical reaction between the pollutant and the liquid. And if the water is a solute, the application limit to ammonia, Cl2, SO2, and NOx. Towers are much more efficient absorbers compared to the scrubber, but get clogged by particulate matter. So there are towers, we will see how these towers are. So you can achieve this even sometime with the bag house filter. The water is sprinkled before just before the bag house filter to remove the gaseous pollutant first, and then that the after that the bag hose filter is used to remove the particle. That combination is also used. So probably say first you can use the scrubber or absorption tower, and then the gas coming out from the absorption tower can be passed through cyclone or bag hose filter to remove the particle. That is also the combination of the control devices can be used. The amount of absorption of non-reactive solution is governed by the partial pressure of the pollutant. Amount of absorption of non-reactive solution, okay, is governed by partial pressure of pollutant. So there could be the reactive liquid like water. There could be some non-reactive solution or non-reactive liquid where the whole absorption will be governed by the partial pressure of the pollutant. Okay, and so there would be no chemical as such chemical reaction as like aqueous phase chemistry. It happens in aqueous phase chemistry, but the chemical reaction will be governed by the partial pressure of the pollutant. The relationship between partial pressure and the concentration of gas in solution is given by Henry's law. So it's a very common law, everybody knows about it. So Pg is the partial pressure of gas in equilibrium with liquid. Kh is the Henry's law constant, and C equilibrium is the concentration of pollutant gas in the liquid phase. Okay, so this is how the partial pressure of the gas in equilibrium with liquid can be calculated, and this will actually govern the removal of or the concentration. So this is the concentration of pollutant gas in the liquid phase, right? So this P partial pressure will actually govern the removal of or the concentration of pollutant in liquid phase. In absorption tower, the liquid introduces in opposite direction to the flue gas. This is called counter current flow. So you can have this is the general you can say mechanism or the operational procedure I have found even for like what I told you about Venturi or Venturi scrubber and absorption column. So always the flow liquid introduces in the opposite direction to the flue gas, and this actually increases the efficiency of the flue gas, the particle removal or
Ma'am,
pollutant removal. Yes.
in this example, the water is solute or solvent. As in the previous slide, they are rating if water is solute, then the application limit to ammonia, chlorine, SO2, and NOx.
Solute means which can dissolve, right?
It is not of a solute and solvent that we discuss in solutions. One is solvent and the other is solute.
Hmm.
So,
Hmm.
ma'am, water is solvent or water is the solute? Means which one is in large amount, the gas or the water?
Ah, okay. Which one is in the large amount? I think that is a very good question. I don't have definite answer about that, but I will just write it here. Maybe I will find out. Okay. But I think it should be water should be. Let me see if it can be explained from any example. Hmm. This is the example for absorption, not absorption. Give me just a moment. I will see in your book, environmental engineering book, maybe.
मैम मुझे मिल गया मैम
Just
मैम
a
मुझे
minute.
मैम मुझे मिल गया
So this is from Cornwall and Davies book. I'm trying to find out where do I have. Yeah, absorption. Then back tower is the energy from Incoming liquid is water free of ammonia. Okay. Kg is 10 grams.
हो गया
Correct the density of ammonia. Determine the height of the backbone of NH3 for the concentration 10 kg per meter cube to a concentration of this. Okay, I think the amount of water has not been mentioned here, but okay, I will find it out because the derivation I did not include in this class. It's a like large derivation. It's a two and a half page. So let me see this. Okay, I will answer it in the next class. Okay. Okay, so adsorption is the similar kind of thing, but here the phenomena is physical bounding between the air pollutant and the absorbent surface. Okay, adsorbent surface. This is the mass transfer process in which gas is bonded to a solid. It is a surface phenomena, right? The gas absorbs it, penetrates into pore of the solid adsorbent. Okay, adsorbate and adsorbent. Activated charcoal, molecular sieve, silica gel, and activated alumina are most common adsorbent. Okay, the bond may be physical or chemical. Electrostatic forces hold the pollutant gas when physical bonding is sufficient. Okay, so there is an electrostatic force which actually applies in order to hold this pollutant. Active carbon can be manufactured from nutshell, coconut, or coal subjected to heat treatment in reducing atmosphere. So this manufacturing of activated coal using the coconut nutshell is very common practice. Even charcoal manufacturing from this sugar cane waste is also very common in Maharashtra. So see how in this way the stubble burning can be reduced, right? We can use this crop waste to produce the activated carbon, and that can be further used in various application, not just the control of air pollution, but it has other applications also. uh, Molecular sieves are dehydrated zeolites. Okay, so these are the alkali metal silicates. Sodium silicate is reacted with the sulfuric acid to make silica gel. Silica gel, you must have used the silica gel, or even if like you have heard about this. And this is simple, the reaction between sodium silicate and the sulfuric acid. And silica gel is very effective moisture removing, you can say, chemical which is used in laboratory as well as in industries. It's very common um, compound. Activated alumina is the porous hydrated aluminum oxide, effective for hydrocarbon pollutants, also effective for H2S and SO2 removal. Large surface area per unit volume is important property of absorbent. The absorbent are ineffective at high temperature and they can be regenerated. So I think you have learnt about Langmuir and Langmuir, you can say, the theory, right? Um, the relation between the amount of the pollutant adsorbed and the equilibrium pressure at constant temperature is called adsorption isotherm. So this is Langmuir equation where the amount of gas per unit mass of absorbent kg per kg can be given by A into Cg upon 1 plus B into Cg, where A and B are the constant, Langmuir constant. Cg is the equilibrium concentration of gas pollutant in gram per meter cube. Cg upon W can be given by 1 plus BC into CJ. So you can see 1 by A plus B by A into CG, right? So versus CG upon W versus CG graph should yield linear relationship, okay? Because this is a linear equation, right? Y is equal to mx y is equal to mx plus c, right? So m is b by a, x is cg, and c intercept is 1 by a. So this should have the linear relationship. B by a is slope of the line, and a by 1 by a would be intercept. Yeah, okay. So this adsorption column, once the gas flows through,
We
or
have another class in like 1 minute.
yes, yes.
I'm saying we have another class in like few seconds.
Oh, what is the time? I'm just
It's
going.
almost 9.
Oh, okay. Okay, I did not see the time. Okay, okay, we will learn about this in the next class, and we will complete it. So I have noted that down, the question regarding solute, right? Whether water is more, or the gas flow rate is more. So regarding the flow rate of gas and water, is that correct? Okay, whoever asked the question, if this is correct, just I will try to find out the answer for that. Thank you very much. Is there anything which I need to explain again, or anything which is not clear? Just tell me if any of you have. Okay, fine.
Ma'am,
Thank
please
you for
upload the slide for
the
air
class.
pollution meteorology.
Stop recording.